I changed some due dates around last night. Lab 3 is due not on Wednesday, but on Sunday. By the way, happy December, everybody. Happy December. Right? Get your Christmas shopping done. Right? Get your mom something nice. You deserve it. All right. Lab 3 is to be worked individually, and you are to submit an individual report. Different than the last two labs. We're not doing group work. This is all individual. Right? There's a video up on YouTube detailing the expectations for the lab. Okay. Then we have mega homework. So I made a decision and I decided to create mega homework. I'm combining homework 6 and homework 7. It is less big, right, than both if you were to have homework 6 and homework 7 separately. So it's less questions, but it's worth double points. Okay. There's still going to be a theory section, and then there's some problems. I posted that on LoudCloud last night. Please take a look at it. That homework is due on the 13th. Okay, you get until the Sunday before the final exam. The final, I mean final in the way that it is the last exam. It's not. It's final exam in the traditional sense. We'll talk about it in a second. Then we've got exam 3 on the 17th. So the last day of class, we're going to take exam 3. Right, exam 3 is the last exam. It's going to cover topic 6. It's not necessarily cumulative, although I think we understand at this point that the whole class builds and you might be asked to make a model of something before you test it in the frequency domain. The benchmark assignment, that's due on the 20th, the very last Sunday of the semester. In LoudCloud, it says it's due the 13th. LoudCloud won't let me change the due date. Turn it in on the 20th. Keep track of it in your head. And then your final presentation also due on the 20th. LoudCloud didn't let me change that. All right, so let's talk about the benchmark for a second. I posted a video with the benchmark expectations on YouTube. Please watch it. We're not going to go through it in class because we only have 3 weeks left, and we spent a large majority of today's class going over exam 2 solutions. Okay, so there's that. Watch it. Ask me any questions that you have about it, office hours, or before or after class after you've watched it. Right. Pretty straightforward. There is a rubric for it. Familiarize yourself with that as well. The presentation is also covered in that video. It is a YouTube presentation, right? So you're not doing it in person. You essentially are going to screen cap yourself doing a presentation and post it to YouTube. You can set it as a private link and then just submit the link with your slides when you submit it. Okay? We can talk about all those things if you have questions after you watch the video. I went over it at the beginning of class. I did tell you guys I had to take my dog to the vet this morning. He is doing fine, like I said, but that means that I have to pick him up at 4 o'clock, and I'm the only one that can pick him up. So office hours are canceled today. Okay. There'll be no office hours today from 3 to 5. I apologize, but that's how it's got to be for today. Okay. You guys have any questions on the things to do? This is the list of everything, right? Everything that's left. Let me go back to Zoom. Everybody doing all right? Yeah, no questions? Okay. Well, in that case, we're going to jump into I don't know where my clicker is. There it is. In that case, we're going to jump into the frequency response analysis stuff, right? So, system analysis in the frequency domain. what do we want to be able to do when we're done with this topic? We want to be able to draw frequency response graphs for transfer functions. We want to determine the steady state response for a sinusoidal input using the graph or the transfer function itself. We want to calculate resonant frequencies and determine bandwidths for systems. We want to evaluate vibration isolation systems for the effects of base motion and rotation on balance. And we want to solve for the steady state behavior of a periodic input when given the Fourier series representation of the input. Now remember the Fourier series, or sorry, the Laplace transform is a very specific case of the Fourier series, right? So it's tied into Laplace transform. Okay. So that's what we want to be able to do, right? So what is frequency response? So far, we have discussed in detail how to analyze systems to several input functions. What are those input functions? What kind of input functions have we been using thus far? Not all at once, guys. Not all at once, please. Was that done? So we talked about sine wave, sure, but that's kind of where we're going to live for right now. We're going to really go dive into sinusoidal inputs with frequency response. We definitely did touch on them. What are the other ones?
Are you referring to like all the way back in like beginning of October, like around the first exam where we had like for each type of like for thermal and like mechanical and springs, like we referring to the different types of methods of inputs? Or are you talking about like?
No, Carl, I'm talking about like if you were building a Simulink model, what kind of blocks would you use to put a signal into your model? No. Impulse and step, sure. Those are definitely two that we talked about. Let's see what's on there. Step, pulse, impulse, and ramp, right? Those were the four that we talked about. Right. We also did use sine wave inputs in some of our Simulink models, right? But we never really talked about how a system behaves due to a sine wave, right? We never did any hand calcs on that. Whenever we use a sine, we always talked about it in terms of Simulink, right? Let's throw a sine wave into this. But what did it actually do, right? It's really important that we understand how to analyze a system's response to periodic or repeating inputs, right? Because these are things like unbalance in rotating machinery. So things like vibration, noise, right? So how do we filter noise in electromechanical systems? Vehicle dynamics and vibrations, right? So automobiles, rockets, and wing flutter due to high-speed aerodynamics. These are all things that deal with vibration. Now, I don't remember if I told you, excuse me, told you guys this story or not, if it was my dynamics class, my MET 213 class. But I'm going to tell it anyway, right? When I was in college, I spent one summer working, or the summer before college, working at an amusement park on the New Jersey shore, okay? I would operate the tilt-a-whirl and the scrambler, in case you guys were wondering. And it's a pretty sweet job, right? But there was one guy who nobody wanted to do his job, and that was the Ferris wheel guy. Okay? Because why? Well, because you have to be really precise with how you load a Ferris wheel. Because if you're not, you can unbalance the Ferris wheel, and then you get a Simpsons situation where the Ferris wheel comes off and it's rolling down the beach, right? Probably not as fun. But yeah, so they had a bunch of high school and college kids doing this, right? So just keep that in mind. But yeah, so rotating unbalance is a pretty big deal, right? The biggest thing that we do every day, every one of us does pretty much every day, is driving our car. That is a series of vibrational inputs into your car. And the shock absorbing system of your car is designed in such a way that that you won't feel every little rough surface on the road, right? Oh, you feel the big ones, but you hopefully don't feel the little ones, right? So how do we model such a thing, right, with repeating inputs? Well, here it is, right? U of t is equal to U, capital U, naught, sine omega t, where U naught is the amplitude and omega is the frequency in radians per second. Hey, we've been using this concept. Right? This is the form that it takes in the Laplace transform table, right? So we've got the amplitude times the sine of omega t, where omega is in radians per second. Okay. Just as a friendly reminder, omega is equal to 2 times pi times f, or f is the frequency in hertz. So if you're given a frequency, so remember, units matter, and if you're given the frequency in hertz, you need to convert it to radians per second. How do we do that? We multiply by 2 pi. So what we're going to talk about, right, is all about how do we handle these sine wave inputs, right? That's really all, that's the only input that we're going to talk about from now on, right? Is everybody okay so far, right? People at home, you're doing all right.
I believe so.
Okay. All right. All right, so if we're given a sinusoidal input, our system's going to oscillate at the natural frequency plus the frequency of the. Okay, so you have some natural dynamics that are going to happen, right? And that's going to be coupled with this input frequency that was given, right? And that's what we call the transient response. And eventually that will settle out, right? And we'll be left with just some steady state response, right? If damping is present, the vibrations of the natural frequency will eventually die out. And my diagram is in a great spot right now, covering all the steps, right? And we can reach a steady state frequency. Yeah. Yeah, this should be better. In case people, actually want to see the text. So if damping is present, our natural dynamics, our natural frequency dies out, and the steady state response oscillates at the input frequency, right? So eventually this natural response dies away, and we're just left with this final sine wave, right? And that oscillates at the same frequency as the input frequency, okay? However, we do end up with a scaling of the amplitude. So my input signal goes into my transfer function. My transfer function pops out y of t. What is frequency response, right? Well, it's defined as the steady state response of the system to a sinusoidal input function. If a linear system is driven by a sine input, then steady state system will output a sinusoidal function at the same frequency. Right? We just talked about that. So you have a linear system, and you give it a sine wave, a sinusoid input, you will get a sinusoid out that is oscillating at the same frequency, right? And in general, the output sinusoid will have a different amplitude, right? So we will end up scaling this sine wave in some way, and we will end up shifting it, right? We will have a phase shift. There will be some phase angle added to it. The nature of the linear system, right, the transfer function, will determine the amplitude ratio, y naught to u naught, right? Remember, where y naught is the output amplitude and u naught is the input amplitude and the phase shift, which we call phi. And both of these quantities are a function of the input. So for frequency response, it's in purple. Now there's a red box around it. Must be important. All that you need to talk about the frequency response is the amplitude ratio and the phase. Turns out that you can plot these two things versus frequency to see how frequency changes both the amplitude ratio and the phase shift. And this creates what we all hopefully have seen before in other classes. This generates our Bode diagram. So we've got Bode magnitude and Bode phase. Bode magnitude tracks how the amplitude ratio changes as a function of frequency. And Bode phase tells you how much phase shift you have as a function of frequency. So next class, we're going to spend most of the time learning how to draw Bode plots by hand-ish. We're going to learn about how to read Bode plots, how to get the data off of it that we need. So, put in some input, right? You put in some input. Goes into my transfer function, then some output comes out, right? Where we've got my input is u naught sine omega t, and my output is now y naught sine omega t plus t. And if you consider the solid line here to be the input, right? The solid line is the input. Let's beef that up a little. That's my input. And the red line's my output. Right? My input, I got my output. Notice the transient response here is not shown. We are going to focus less on drawing the transient response in this case because you get some weird dynamics. You guys might remember from your homework some of the ones that you put sine waves in, you get this like crazy oscillations to start, and then that dies out and you're just left with the damp sinusoid, right? We're not going to worry so much about drawing the transient portion of the response. We're going to be more worried about what happens at steady state. So if you look at these, right, and you take the peak to peak time here, right, this is my phase shift, right? So you can see what has happened. If I put this through this transfer function, I get a scaling of my amplitude, right? the magnitude of my sine wave has decreased, and I have shifted it in time. Right? And I have shifted it in time. And in this case, I've lagged it, right? Because my output lags behind, happens after my input, right? Happens after my input, it's lagged. How much time shift do we have? This much time shift. Your phase angle divided by the frequency. That's how much time you phase shifted. How much time shifted. All right. Any questions so far? Everybody doing all right? You're tracking. You're good. Okay. So what about the transfer function? Talk about it. So let's consider the following third order system. So what if I had an exponential input? Let's assume for a second I have this exponential input u of s times e to the st, where s is sigma plus j omega, right? It's a complex variable, right? So sigma is my real portion and omega is my imaginary portion. If sigma was equal to 0, then s would equal to j omega, and the input will become mu of j omega, right? So I just plugged in j omega for s. Right? That's what I did. Well, by using Euler's theorems, right, I can take this e to the j omega t, and I can rewrite that as cosine omega t plus j omega t, or j sine omega t. Right, so Euler's theorem allowed me to take that exponential and rewrite it in terms of sine and cosine in the imaginary plane, the real imaginary. Okay. We didn't go over Euler's theorems explicitly, but we did talk about them in passing when we were talking about transfer functions. Okay. Why is it that that works, right? So assume for a second, right, the complex plane representation of e to the j omega t. And we use Euler's theorem here. And if I'm in the real imaginary plane, right, this describes some vector, right? Some vector in the real imaginary plane. Well, the angle between this vector and the real axis is omega times t. And the real portion is the cosine of that angle, and the imaginary portion is the sine of that angle. Okay. So if the input u of t is u j omega e to the j omega t, then the steady state particular solution is y of j omega e to the j omega t, and it is a complex function. Not complex, but complex. Complex. Okay. So by using Euler's theorem, right, and this is nice. This is nice. We now have everything in j omega. Okay. So here's our system equation, right, that we were given. Or I can rewrite this as, the transfer function, right? So I just took this equation that I had, and I took the Laplace transform with 0 initial conditions, and I created y of s over u of s, right? And I'm left with this: 2s plus 3 over s cubed plus 4s squared plus 12s plus 26. This gives me characteristic roots. Oops, sorry. Gives me characteristic roots of negative 2.932 and minus 0.534 plus or minus 2.93j. Right? So we know that the transient response dies out at steady state, right? Because we have a stable system. We know this is stable. How do we know that this is stable? Well, we have negative real portion roots. That means that my transient response is going to go away because the exponential will decay. And we'll be left with something at steady state, right? Steady state value. So if we substitute the exponential input and output equations into our differential equation, right? So remember we said that y is equal to y of j omega e to the j omega t, right? So we're just going to take the derivatives of those, and we solved for u of j omega, right, on the previous. And so we're just taking these and we're substituting these in to our equation, right? We're giving it the differential equation treatment. We're giving it the differential equation treatment. So remember, going back to the last slide, right, or right here. So we said u of t is equal to u of j omega e to the j omega t, right? And we take the derivative once because we have a u dot in there. And we're going to plug u in for u of t and u dot in for u dot, right? And we know that y of t is equal to y of j omega e to the j omega t. So we have to take the derivative 3 times, right? And that's what we're getting at. And if we do that, we get the result on the bottom here, right? We're now, instead of s's, right, I've got j omega, right? So I've got j omega cubed plus 4 times j omega squared plus 12 j omega plus 26. Y of j omega e to the j omega t. Well, hey, if I plug this other stuff into the other side, something very interesting happens here, right? Those exponential terms get lost, right? They cancel. I've got e to the j omega t on both sides, so those are gonna cancel. And if you're thinking to yourself, well, Dr. D, that looks an awful lot like how we find the normal transfer function, except that instead of s's, you're going to use j omega. Yes, you're right there. Yes. Right. So okay, I've got this thing, right? We're gonna make our transfer function, right? I need y of s, I need y of j omega over u of j omega. Right? So there's the equation again. All right, I'm gonna form this. Okay, look, if I do all this, right, these guys cancel. I just talked about that. That cancels. Cross multiply, cross divide, whatever you want to call it. Hey, again, it looks exactly like the transfer function we had on the previous page, except that we have j omega instead of s. So, Dr. D, why did you go through the whole derivation if that's all that it was? Good question. Why? Well, we want to understand how we got there, because when we start trying to calculate magnitudes and phases, we need to understand what it looks like in the complex plane. Okay. So I have some function of j omega entering, and I'll have some function of j omega leaf. Right, so here's my sinusoidal transfer function. Y of j omega over u of j omega. That's the sinusoidal transfer function. What if I had, right, and look, right, here it is for comparison. So when you're asked for the sinusoidal transfer function, because you will be asked for the sinusoidal transfer function, when you are, you should find the regular transfer function and substitute j omega in for s. That's how I would do it. Because doing that derivation is great, but that's more of a, now you understand where it came from and why it works, and we know what it is. That's what I would do. So why would we do that, right? That's a good question, and we're going to get there in a second. Hold your horses, right? But there's a specific reason why we want this as a sinusoidal transfer function, and it has to go back to magnitude and phase plots. We want to understand the magnitude and the phase of our system. So why do we want to understand that? Man, you guys are asking all these questions. We're going to get there. Be patient. Be patient. Is everybody okay with this as is so far? We're tracking, we're good. So far, not too bad, right? You find the transfer function and you plug in the j omegas, right? So we always talk about magnitude and phase, right? Magnitude and phase in our Bode plot. So how do we calculate this, right? Well, the magnitude is the magnitude of the transfer function. Okay? The magnitude is the magnitude of the transfer function. So imagine for a second that the transfer function gives you some, if you analyze the transfer function at a specific frequency, this will give you some vector in the real and imaginary plane, right? Like the one we see here. If you wanted the magnitude of the vector, what would you do? You would use Pythagorean theorem, right? And you would find the result. It's a similar concept. Right? What about the angle? If I wanted this angle phi, right? Because this angle phi is just my phase angle. Well, that's the tan inverse of the imaginary portion divided by the real portion. Okay? And sometimes you'll see this as taking polar form, right? Polar form. G of j omega is equal to the magnitude of G of j omega times e to the j phi. Sometimes it's given in form. That's fine. But the important thing is to know, how do we calculate magnitude and phase? Now, is it that easy? Do you just find the transfer function and take the square root of the sum of the squares, and you just Pythagoras the crap out of it? Mm-hmm. Yeah, pretty much. It is that easy, but so let me ask you this. Say I had a fraction, and the fraction was like, I don't know, make it easy. 100 over 25, and I take the square root of it. Isn't that the same as me taking the square root of 100 divided by the square root of 25? Can I analyze the numerator and the denominator of something the same one? Can I take the Pythagorean theorem of the numerator and the denominator if there's two separate functions? The answer is yes. Okay. We're going to talk about that in a second. So we want to derive an equation for the frequency response that will give us the steady state output for the system. That's what we want, right? We want to know, that's our ultimate goal, right? Is we just want to be able to get steady, like what is the steady state response, right? All right, so for a steady state output, right, we would get something like this, where we would get y of steady state is equal to y of j omega e to the j omega t, right? But remember, y of j omega, right? Look at this block diagram up here. Right? If I multiply g of j omega times my input, I will get my output, right? That's the whole deal with the transfer function. Transfer function times the input gives me the output, right? So I'm just rewriting y of j omega as g of j omega times u of j omega. So my transfer function, my sinusoidal transfer function, times the inputs, the sinusoidal input, times e of j omega t. Okay, let's take a look at this, right? Because remember, we just went over this in polar form. So if we go back here, in polar form, I can rewrite this as the magnitude times e to the j t, right? So I'm going to rewrite that in polar form. I rewrite this in polar. Again, why you do this, right? Why can't we just leave it? Polar form is nice because it relates it back to the magnitude and the phase form, right? Because I said at the beginning when we started this that everything is related to magnitude and phase in some way as a frequency, as a function of frequency.
Dr. D,
Yeah.
someone needs back in the class.
So here we are. It's a function. So we massaged it a little bit, right? So I take that and I plug in g, magnitude of g of j omega e to the j t. Well, I can combine those exponentials, right? Because if I multiply two exponentials together, it's like adding the exponents, right? Now this looks interesting, right? Because I've got g of j omega times u of j omega. And so this is, remember, this is the magnitude, right? These bars indicate that that's the magnitude of my transfer function times the input function times e to the j omega t plus t. Okay. So if I let the sinusoidal input be an actual sine function, right, and I use the imaginary part, because at steady state, the real part will go away, right? Because the real part is defined by my exponential. Then I'm left with this. And this is the equation. This is the equation for my steady state output given a sinusoidal input. What if I was given a cosine input? Well, then it's a cosine output. Okay. So at steady state, given a sine wave, it's the magnitude of my transfer function times the original amplitude of my sine wave and the frequency that's shifted by theta. So when we apply a sinusoidal input to a system, we will get a scaling of the amplitude and the phase shift. How do we calculate the magnitude? Pythagorean theorem. How do we calculate phi? What's the tan inverse of the imaginary over the real? Okay. Anybody have any questions? Everybody doing all right? Nothing. Everybody's good. There it is again in the box too. There's one more. Right now, we already said this, right? What if you had a cosine input, right? You're always going to take the imaginary. I'm sorry, if you have a cosine input, you're going to use the real part. Okay? So another way of thinking about it is this, right? If you started with a sine, you're going to keep the sine. And if you started with a cosine, you should keep the cosine. Okay? What if I shift by like 90 degrees? Well, then it means you just shifted into a sine or a cosine, right? From one to the other. So this is the equation. Right? This is the equation. You were asked to find the steady state response of a system, use that equation. Now we just have to figure out how do we calculate the magnitude and the phase angle, right? That's what we need to figure out. So, if you put in a sine wave to a system, you will get a sine wave out. It will have the same frequency, it will be shifted, and it will have a scaled input. The magnitude of G of J omega is the magnitude of Y of J omega divided by the magnitude of U of J omega. And phi is the argument of G of J omega, which is just the tan inverse of the imaginary portion divided by the real portion. Okay. Let's talk a little bit more. Well, let's just try one. Well, let's do one by example. This will be where we, after this, we'll cut this. Right? Running out of space. Okay. So I'm supposed to determine the frequency response, right? I'm told that I have a sinusoidal input voltage, right, described by 2 sine 50t that's going through this RL circuit. Okay. I'm just gonna put my truths and my inputs and outputs right here. Well, I've got KVL, E of t is equal to ER plus EL. Oh, you don't really need to use impedance for this. It doesn't really help us in any way. Yeah, you could use impedance, right? Because the impedance should give you the transfer function right off the bat. Yeah. It's up to you. This one's not too bad to use without impedance. We've done it quite a few times. So let's reduce it. If I do my reduction, I use my KVL. KVL is going to tell me that En of T is equal to Li dot L plus R I sub L. And there it is. But I want to put it into standard form, right? This is a first order system. I want to put it into a first order standard form, which means I need to clear my I sub L variable, which is going to give me L over R, I dot L, plus I sub L, equal to 1 over R En T. Which is nice because we have standard form, right? I already know that my time constant has to be L over R, which we're both given. And will tell me that my time constant is 0.0167 seconds, which means 4 times tau, or settling time, is equal to 0.067 seconds. That's pretty fast. It's a circuit, so we would expect it. Let's take the Laplace transform of this. Right, because remember, I need the transfer function, right? If I have the transfer function, then finding the sinusoidal transfer function is a snap. So if I take the Laplace transform, I'll get L over R S plus 1 IL of S is equal to 1 over R En S. So my transfer function, IL of S over E of S equal to 1 over R divided by tau S plus 1. All right, I just substituted in tau for L over R. We'll say that this is equal to G of S. Now that's great. That's great, right? Because what were we asked for, right? We were asked to find what were we asked for, right? We were asked to find a steady state response, right? Is that what we were asked for? Determine the frequency response. Okay, so if you're asked to find the frequency response, right, this is asking you for the steady state response of the system. Okay. Okay, so let's continue on. So my transfer function G of S is equal to 1 over 0.02 S plus 1.2. What did I do? I substituted in my 1.2 ohms for R, and I substituted in for tau. Right? That's what I did. So now, right, in this case, I sub L, steady state, has to equal the magnitude of G of J omega, right? This is from our equation, not plus, times U naught sine of omega t plus t, right? That's the equation that we had on like 3 different slides in a row. It must be an important equation. Looking at the master sheet, it is the very first equation under frequency domain response. That's the very first one on the frequency domain response. And that's followed by magnitude and phase. And then finally, you've got some transmissibility and resonant frequency. So we need to figure some things out. Now remember, E in of t, and let me write it with the lowercase, E in of t was equal to 2 sine of 50t. That's omega. That 50 is omega. And this is u naught. So I need to figure out j or g of j, the magnitude of g of j omega, right? Well, let's write g of j omega. Okay. So remember, if you want g of j omega, just substitute in j omega for s, right? Easy peasy. Now what? Now what? I want the magnitude. So I need the magnitude of the top and the magnitude of the bottom. Well, the magnitude of the top is the real plus the imaginary squared square root, right? There's a zero imaginary part on the top, right? So that's what we have. And last time I checked, the square root of 1 squared was just going to be 1, right? What about on the bottom? Well, you take the Pythagorean theorem. The real part is 1.2. The imaginary part is 0.02, right? Square root of 1.2 squared plus 0.02 squared is 1.2. 1 over 1.2, 0.833. This is the magnitude of g of j. This is the magnitude. Where did the j go, Dr. D? Remember, when we're in the real and imaginary plane, j indicates that you have an imaginary component. It doesn't stay in when we take the magnitude. The magnitude only cares about how much do we have. What is the resultant of this vector, right? Think of it, each part of this fraction as a vector in the real and imaginary axes, right? So the top part I will draw in red. This goes out to 1, right? The imaginary part has a vector that is 0.02 in the imaginary and 1.2, right? We want this vector, right? You're given, think of it this way, in terms of vectors, right? You're given the components and you want the resultant of the numerator and the resultant of the denominator, okay? 0.833. So we'll hang on to that. Now we just need phi, right? Well, Dr. D said that phi is equal to the tan inverse of the imaginary over the real minus, right, so we'll go over this, the imaginary over the real. Now, why is it subtracting? Why is it subtracting? It's a great question. Explain it in a second. All right, so what's the tan of 0? All right, well, isn't that just 0? Tan inverse of 0? I hope so. Otherwise, I'm a liar. Nailed it. Tan inverse of 0.02 over 1.2. So now I've got all the parts. I need to put this all together. Oh, don't want to do that yet. Well, just put it down here. So ILSS is equal to 0.833 times U naught, which is 2, times the sine of 50 t minus 0.0167. Right, so 2 times 0.833 is 1.667. 1.67. What's that? Man. So why is this subtracting, right? Because remember, it's really this. If we were to write this in polar, right? Remember that both, remember the magnitude, right? This g of j omega is actually y of j omega. I didn't give myself enough room. I'll write it on the next slide. So let's look at the input. Let's look at what happens, right? Here's a plot. Here's a plot. Okay. Here's the bold line, right? The solid line is my input. The dashed line is my output. Right? We scaled it and we had a phase shift. Scaled it and we had a phase shift. Okay. Why is it subtracting? Because remember, it's actually, if we write it in polar, don't want to do that. It's really this, right? Really this, right? It's some angle phi that defines both of these vectors in the real and imaginary plane, right? We can write both of these in polar. And if you divide exponents, it's the same as subtracting. Right? So phi is actually phi1 minus phi2. Right? Or why don't we call it pn for numerator and phi d for denominator. All right. Oh. Good. When you're doing these, make sure your calculator is working. Especially when you're doing your tan inverses, right? Put it in degrees. No, it's gonna come out poorly. So make sure you got everything in radians. You guys have any questions? If you wanted to, you could throw this in the Simulink on your own. It's not super complicated and play around with it. If you want it. If nobody's got any questions, then that's it. Next class, we will continue with a couple of problems, right? And we'll jump into how to draw bogey plots. Right?
Dr. D,
Yes.
is the third exam going to be like testimonials the same way?
Likely.
Cool. Thank you.
Hey, what's going on, Dr. D?
Thank you. Have a good one.
Still no office hours today?